Okay, moving into material from chapter 14. Primary topic in chapter 14 is equilibria, or chemical equilibrium. And we've talked about this a little bit as we've kind of hit on this issue in some of the last couple chapters. An equilibrium is a situation where a reaction is happening in both directions. It's happening from reactants to products and also from products to reactants. And when a system is at equilibrium, there's a balance there where the forward and backward reactions are happening at rates that keep the concentrations of all the components the same. So this is a special kind of system, and we want to look into how we can calculate information about this type of system. Now, the first thing we want to do to describe what's going on here is understand how to write an equilibrium constant expression. So there's a constant that goes along with an equilibrium for every reaction. That's going to be the basis for almost every problem that we're going to look at here. So if we imagine kind of a generic reaction, so let's say we have lowercase a moles of reactant A reacting with lowercase b moles of reactant B, and this is in equilibrium with lowercase c moles of product C. So what I drew here is an equilibrium arrow with the arrows going in both directions at the same time, different from the one-way arrow that describes just kind of a one-way reaction. Now the equilibrium constant is abbreviated with capital K, so keep that in mind. Rate constant's lowercase k, equilibrium constant is capital K, right? They're similar, but they're certainly different, so we need to keep track of which one we're actually describing. The way we define an equilibrium constant is that it is the concentration of the products of a reaction divided by the concentration of the reactants of a reaction. And with regard to this equation, generic equation that I have here, the product is C. So we have the concentration of compound C. Now each concentration is going to be raised to the exponent that corresponds to the stoichiometric coefficient. So this would be C to the Cth power. The reactants are both A, so we'd have the concentration of A, and multiplied by the concentration of B, they would both also be raised to an exponent that corresponds to their stoichiometric coefficient. Okay. Now, we should be able to do this for any reaction that is in equilibrium. Draw out a equation that's going to relate K to the concentrations. Again, that's generally called the equilibrium constant or equilibrium constant expression. Now, there are some rules here that make this maybe a little trickier than what we've described so far, and that is that whether a component appears in the equilibrium constant expression is based on its phase. So in order for a component to appear in the equilibrium constant expression, the concentration has to change. So concentration has to change as the equilibrium is established. So if the reaction shifts one way, is that going to change the concentrations of the products and reactants versus shifting the other way and changing them in the opposite direction? So as a result, solids do not appear in equilibrium constant expressions because you can't change the concentration of a solid. You can only change how much there is. The same is true for pure liquids. So no solids, no liquids in the equilibrium constant expression. Aqueous solutions, and gases will appear in equilibrium constant expressions, but anything that's solid or a liquid, we're going to leave out. So AQ, G, those will appear. Anything that we see as S or L in the equilibrium constant expression will not. So a few examples here. First reaction here, we've got 3 moles of NO in equilibrium with a mole of N2O and a mole of NO2. So the equilibrium constant expression for that reaction would be the products. So we have 1 mole of N2O, so concentration of N2O. Now that would be to the first power. We generally aren't going to write in the ones, but just for clarity here, I'll do it on this one. 1 mole there, so that would also be to the first power. On the bottom of this equilibrium constant expression would be the reactants. So again, products over reactants always. So NO, there's 3 moles of NO though, so we would want to raise that one to the third power. Now, in this case, if I'm using concentrations as technically as a Kc, or a concentration-based equilibrium constant, when a reaction is all gases, you could write what's called a Kp, which would be a pressure-based equilibrium constant. And in that case, you'd use the partial pressure of each of the gases, but you'd get exactly the same form. It'd be the pressure of pressure of N2O, pressure of NO2, and then the pressure of NO would be cubed in that expression as well. So, next reaction, right? Again, we've got reactants, products, they're all gases, so they will all appear in the equilibrium constant expression. So if I start on top, that would be the products. 1 mole of carbon disulfide, 4 moles of hydrogen. So I'm going to raise the concentration of hydrogen to the 4th power. Methane and hydrogen sulfide are the reactants, just 1 mole of methane, so just that concentration, but 2 moles of hydrogen sulfide, so that concentration will be squared or raised to the 2nd power. Okay, now the third example here, we start to see there's a solid here in this equation, so the gas phase components will appear in the equilibrium constant expression, the solid will not. So the equilibrium constant here, the only product we would include is the carbon monoxide. That would be raised to the 4th power. The reactant is also gas phase, so that will appear as well, but because there's no stoichiometric coefficient, right, we just have that concentration raised to the 1st power. Okay, now the last reaction, we have a liquid. Now, this reaction is a little strange. Because gases reacting with liquids is kind of unusual. This would be more common if these were aqueous and this was a liquid. So a reaction occurring in aqueous solution, the concentration of water can't change. Water would still be a pure liquid. We would leave it out of that equilibrium constant expression. And the same would be true here. The gases can change concentration. They'll show up. The pure liquid cannot. So the water would not appear in this equilibrium constant expression. Product C2H6. That would be raised to the 2nd power because of that stoichiometric coefficient. Multiply that by the concentration of oxygen. And then the only reactant we would include is the C2H4. And that would also be raised to the 2nd power because of the stoichiometric coefficient. Okay? So watch out for your solids, watch out for your liquids. Otherwise, right, this is fairly straightforward. But this equilibrium constant expression is involved in almost every problem. So if you don't know how to do this, you're going to have trouble with pretty much every problem we'll encounter in the next 3 chapters, because we have 3 chapters in a row based on equilibrium. Now, what does K tell us about what is going on in the reaction? There's really 3 possibilities we should consider. One is that K is large, so I'm going to use 2 greater than signs. So K greater than 1, so big. And then let's look at the opposite, which is K is very small, so less than 1, or quite a bit less than 1. Now, if I look at this expression, this will help me understand what these mean. If K is very large, that would mean the concentrations of the components here in the numerator of the fraction are high compared to the concentration of the species here in the denominator, or the bottom of the fraction. So that means I've got a lot of products, very little reactants when this system is at equilibrium. So a very large value of K is what we might refer to as a product-favored equilibrium, meaning there's a lot of product present, there's very little reactant present when the system's at equilibrium. K being very small, of course, is just the opposite. If we have a large number on the bottom of a fraction relative to small numbers on top of the fraction, that would give us a very small number. So if K is very small, that means this equilibrium is reactant favored, meaning at equilibrium there's a lot of the reactant, there's very little of the products in this system. And of course the other possibility would be K is, in the vicinity of 1. That's going to be relatively similar concentrations of products and reactants. Now, it's not going to be necessarily equal because we don't have the same number of components on the top and bottom of the fraction. But if K is in the vicinity of 1, then we do have fairly even amounts of both product and reactant when the system is at equilibrium. Now, the last thing on this page is a very similar idea, but one that we'll use as we start to solve problems, and that's this concept or quantity called the reaction quotient, or Q. And what it means, Q is defined exactly the same way as K is. It's the concentration of the products over the concentration of the reactants, right? Or again, if it's gases, it would be the partial pressure of the products over the partial pressure of the reactants. But Q is specifically for a system not at equilibrium. And so if we have a mixture of components and we want to figure out what's going to happen as that system moves towards equilibrium, what we can do is calculate Q. And then we can compare the value of Q to the value for K, the equilibrium constant. That will tell us which components would need to increase in concentration, which components would need to decrease in concentration, and we'd be able to determine, will the reaction shift toward the products or shift toward the reactants as it approaches equilibrium. That is what we will look at in the next couple of problems.